halides, and for episode 2 we will discuss about the preparation of alkyl halides. Before we take up the preparation of alkyl halides, let's recall what we did in our previous session about alkyl halides. So, the importance of alkyl halides and their everyday uses were taken up. The alkyl halides are used as solvents, fire extinguishers, anesthetics, pesticides, and many more uses like medicine, etc. Then the classification of alkyl halides into primary, secondary and tertiary was dealt. The nomenclature of alkyl halides by substitutive and functional class methods was done, and also the IUPAC nomenclature was discussed. An introductory remark was done about the preparation of alkyl halides from alkane, alkene and alcohols. So, the lecture plan for today is that we would deal about the preparation of alkyl halides from alkanes by radical halogenation, and in radical halogenation of alkanes the advantages and disadvantages of preparation would be discussed, and then the preparation of alkyl halides from alcohols using primary, secondary and tertiary alcohols will be in details, and the mechanistic details of all the reactions which come across during the preparation of alkyl halides by alkanes and alcohols will also be discussed. After the mechanistic details of the reactions, we would sum up the lecture for this particular session. So, we start with the preparation of alkyl halides from alkanes. Alkyl halides can be prepared from alkanes by making the alkanes react with Cl2 or Br2 readily in presence of sunlight to form haloalkanes by a substitution reaction. For example, methane reacts with chlorine molecule in presence of sunlight to form chloromethane and hydrogen chloride. However, this reaction does not take place in dark and gives a mixture of products. So, if we use more chlorine, a mixture of dichloromethane or methylene chloride, trichloromethane or chloroform and tetrachloromethane or carbon tetrachloride is obtained. We can obtain pure chloromethane or tetrachloromethane by using excess of methane or chlorine respectively. That means if we use excess of methane, we will get the formation of chloromethane, and if we use excess of chlorine, we will get tetrachloromethane. And the other products, because it's a mixture of products which is obtained, therefore other products can be obtained by distillation of partially chlorinated mixtures. So, what happens when there are multiple products which are formed during the reaction of alkane with halogens? The reactions go like this. Methane reacts with a molecule of chlorine in presence of light and forms a mono-substituted product, that is methyl chloride, and of course, hydrogen chloride is obtained as the byproduct. The methyl chloride further reacts with chlorine molecule again in presence of light and gives dichloromethane. Dichloromethane in presence of chlorine gives trichloromethane, and finally, the trichloromethane reacts with more of excess of chlorine to form tetrachloromethane. The halogenation of alkanes involves radical chain mechanism, and as you studied earlier also, the radical chain mechanism involves 3 steps: initiation, propagation and termination. The preparation of radicals can be initiated in presence of heat or light only, and you would remember that the reaction does not take place in dark. So, the first step of this radical halogenation is initiation, by which formation of radicals takes place from non-radical species. And in the initiation process, the first step involves homolytic dissociation of the halogen molecule. We've taken an example of chlorine here. So, you are aware of homolytic dissociation, wherein each atom gets an electron by the shared pair which forms a bond between these two atoms. So, in presence of sunlight, we get 2 chlorine radicals. This is the first step of initiation process. In the propagation process, this is the second stage of radical chain mechanism. There are 2 repeating steps. So, steps 2 and 3 involve formation of more radicals. So, methane, for example, reacts with the chlorine radical, forms hydrogen chloride and generates the methyl radical. The methyl radical further reacts with the excess chlorine which is in the reaction mixture and gives another chlorine radical and forms methyl chloride. The last process of radical chain mechanism is termination, which involves combining or destructing of the radicals. The radicals may combine with each other, which we may call that the radicals are being destructed also. So, 2 methyl radicals which are generated in the propagation step combine to form a ethane molecule, or else the chlorine radical may combine with a methyl radical and form methyl chloride. Similarly, 2 chlorine radicals can also combine with each other and form a chlorine molecule. There is another reaction which takes place when halogenation of alkanes takes place in presence of sunlight, and that is disproportionation reaction. In disproportionation reaction, there is formation of an alkane and alkene during the termination step. Otherwise, when there are 2 radicals present, there is a possibility that these 2 radicals will combine, as was shown in the previous slide, and give rise to another alkane molecule. But in disproportionation reaction, there is formation of one alkane and another alkene, that is an unsaturated hydrocarbon. So, what happens when the products are formed during the halogenation of alkanes? There is a possibility that the alkane has 2 types of hydrogen atoms. Therefore, there is a possibility of formation of 2 products in different ratio. If we take this example, butane reacts with chlorine in presence of sunlight and gives 30% of the 1-chloro product and 70% of the one which is substituted at the second carbon. Similarly, 2-methyl propane reacts with chlorine and gives either substitution at the tertiary carbon or substitution at the primary carbon. So, we have to look for reasons why does it form 2 types of products and why are they formed in different ratios. So, experiments have indicated that substitution at tertiary carbon is preferred over both secondary and primary carbons. So, monobromination of 2-methyl pentane is very regioselective and forms almost exclusively 2-bromo-2-methyl pentane. This is the reaction where we have 2-methyl pentane reacts with bromine and in presence of light gives us exclusively the 2-bromo product. We call this reaction as a regioselective reaction because there was a possibility of formation of a 1-bromo product also, but because of the reasons which we shall discuss further, the formation of only one product takes place. And regioselectivity has been observed more for bromine than for chlorine. So, the order of reactivity in case of alkanes goes by the stability of that particular alkane, and it has been observed that primary alkanes are less reactive as compared to secondary, which are lesser reactive as compared to the tertiary alkanes. The order of stability of the free radical also goes in the same sequence, that is, the primary radical is less stable as compared to secondary, which is less stable as compared to tertiary. Therefore, the order of reactivity of alkanes during halogenation is that the tertiary reacts the fastest, and that is the product which is formed in maximum amounts. So, when we prepare alkyl halides from alkanes, there are a number of advantages. The biggest advantage of this reaction is that it is very useful for the industry due to the cheap reagents which are used in the reaction, and the mixture of products can be separated by distillation. It's very easy to distill all the byproducts which are obtained, which can be used for further synthesis in the organic chemistry. So, each of the individual products is sold separately. Therefore, it's very advantageous for the industry. But we have a few disadvantages for this reaction. That is, laboratory synthesis are generally limited to specialized compounds that give a single major product. So, free radical halogenation rarely provides good selectivity and yield, and for any reaction, yield becomes one of the very important parameters for taking it for a larger scale. A few more disadvantages of this method is that it usually produces mixture of products, as you saw earlier, due to different kinds of hydrogen atoms that can be abstracted. And more than one hydrogen atom may react, giving various products because of multiple substitutions. So, if we use excess of halogen, then we get the higher order of the halogenated product, and also because of varying nature of hydrogen atoms, the possibility of substitution at different carbons is also there, and it therefore gives us a disadvantage. So, this was as far as the preparation of alkyl halides from alkanes was concerned. Alkyl halides can be prepared from alcohols too, and in case of alcohols, most generally useful method is the one where alcohol is treated with the hydrohalic acid, that is HCl, HBr and HI. Here again, the way we saw in the case of alkanes, tertiary alcohols find the highest activity as compared to secondary and primary. The primary is the least reactive and reacts only at higher temperature. So, if we look at this general reaction, this is a tertiary alcohol. When it reacts with the hydrogen halide, it gives the tertiary substituted halogen, and of course, this is water molecule. So, the ease of reaction with tertiary alcohol can be seen also in this example, where we use the methyl hexanol. We have a tertiary carbon here, which when treated with HCl at 0 degree centigrade, we get the tertiary carbon substituted chloro compound, and this is almost in 90% of the yield. So, similar to the case of alkanes, what we find here is that the tertiary alcohols find maximum reactivity. Methyl alcohol, which does not have a carbon or an alkyl group adjacent to it, is the least reactive, which is less reactive as compared to the primary alcohol. Primary alcohol is the one which has one alkyl group attached to it, which is lesser reactive as compared to secondary alcohol, and then which is again lesser reactive as compared to tertiary alcohol. If we look into the mechanism of the preparation of alkyl halides from tertiary alcohols, we will notice that these undergo the nucleophilic substitution reaction SN1, and you would recall from the substitution reactions which you studied earlier that SN1 is called nucleophilic substitution unimolecular. And in this particular mechanism, the first step involves addition of a proton to water molecule, because most of these reactions are aqueous, done in presence of water, and there is formation of hydronium ion, as can be seen in this reaction, water reacts with the molecule of HBr, and this H being acidic is being taken up by the water molecule and a hydronium ion is produced. As a result, we get a nucleophile in the form of bromide ion. So, here you will have to recall the terms nucleophile and electrophile. Nucleophile is the one which is nucleus loving, that is, it is looking for a positive center. So, in the first step of this SN1 mechanism, the alcohol, tertiary alcohol reacts with the hydronium ion, and this hydroxyl, the lone pair at oxygen, picks up this proton, which gives the formation of water, and this is the oxonium ion which is formed in this step, and this reaction is actually a very rapid reaction. It is reversible also, and very quickly this reaction gets back to the tertiary alcohol and the hydronium ion. In the second step of this mechanism, breaking of bond takes place to give stable molecules or ions. Therefore, formation of a tertiary carbocation takes place, which is an intermediate, and a water molecule is lost. So, here you can see this is oxonium ion which gets converted into a stable intermediate, a tertiary carbocation and a water molecule. Then finally, in the third step, making of a new bond between nucleophile and an electrophile takes place, and as we know that tertiary carbocation is an electrophile, bromide ion is the nucleophile, which combine together to give us the final product, and that is alkyl halide. So, we name this alkyl halide as 2-bromo-2-methyl propane. So, this is the SN1 mechanism. What happens in case of primary and secondary alcohols is that they are converted into bromoalkanes and iodoalkanes by treatment with hydrobromic and hydroiodic acids, and the example is here. 1-butanol reacts with HBr. This is on refluxing it with this aqueous solution, and we get the formation of 1-bromobutane. So, this reaction is quite smooth, but in case of primary alcohols, we notice that there is SN2 mechanism which is followed. In the first step of this SN2 mechanism, addition of proton transfer and to form an oxonium ion similar to the one which we saw in case of SN1 mechanism. Once the oxonium ion is formed, there is formation of OH2. Now, this OH2, that is a part of oxonium ion, it is a very good leaving group, and because of this, the reaction is substitution nucleophilic bimolecular, that is, the reaction takes place by simultaneous bond breaking and bond making to give stable molecules. So, in the second step of this reaction, formation of a new bond between a nucleophile and an electrophile takes place. You know that bromide ion is the nucleophile and this is the electrophile which we have. So, what happens is bromide ion attacks this carbon, and OH2 being a very good leaving group, it immediately and simultaneously leaves, resulting into the nucleophilic displacement of water by bromine and formation of bromoalkane. So, this is by the primary alcohols. In case of secondary alcohols, the most widely used reaction is carried out with SOCl2 or PBr3 or PBr5. That itself shows that the reaction takes place under little rigorous conditions, because SOCl2 and the phosphorus tri and pentabromides are very good reagents which are able to displace this hydroxy group and give us the halogenated product. Similarly, we have another example. 2-butanol reacts with phosphorus tribromide to give us 2-bromobutanol, which is obtained in good yields. So, the reaction of alcohols with alkyl halide in presence of zinc chloride gives us a very good reaction for testing and differentiating between the primary, secondary and tertiary alcohols. We call it as Lucas test. The Lucas reagent is Rx with zinc chloride. Zinc chloride is used as the catalyst here, and reaction of primary, secondary and tertiary alcohols with Lucas reagent is used to differentiate amongst the three types of alcohols. So, the low molecular weight alcohols are soluble in the Lucas reagent, but not the alkyl halide. Therefore, what happens at room temperature, the solution turns cloudy immediately for tertiary alcohols, turns cloudy in about 5 minutes for secondary alcohols and remains clear for primary alcohol. So, this is the way we can differentiate the three types of alcohols, making use of the reaction of preparation of alkyl halides by using these alcohols and the hydrohalic acids. So, let us summarize what all has been dealt in this particular lecture of the lecture series on alkyl halides. We talked about the preparation of alkyl halides from alkanes, and we saw how this reaction takes place in presence of light. Therefore, this reaction follows a free radical mechanism. Then we also saw how is this reaction of alkyl halides preparation is advantageous to industry and disadvantageous also. Then we have seen that the preparation of alkyl halides can be done using alcohols, and the tertiary alcohols undergo SN1 mechanism, whereas the primary alcohols show SN2 mechanism, and the secondary alcohols, these are when treated with SOCl2 or phosphorus pentabromide or tribromide, give rise to the formation of alkyl halides. So, in our next session of alkyl halide preparation, we will see how alkyl halides can be prepared using alkenes and how important is allylic substitution in case of alkanes. Thank you.